Welcome to this deep dive. When we look at a perfectly tuned sports car, there's this expectation of magic.
Oh, absolutely.
Yeah, we see the smooth, effortless movement and we just think it's all grace and precision. But if you zoom in, like under a microscope, it's actually a brutally high-stress environment of metal grinding against metal.
It is a totally violent environment. I mean, we love the quiet hum of a finished engine, but we completely ignore the extreme physical torture the metal had to endure just to get there in the first place.
Right, exactly. So today, our mission is to take you behind the scenes of that mechanical torture chamber. We're translating 5 critical manufacturing terms from this dense jargon to show you exactly how the everyday machines you rely on survive those extremes.
Because to even build a machine, you have to, carve out the fundamental components first.
Huh.
Think about drilling a tunnel deep through the center of a solid steel shaft.
Okay.
The deeper you go, the less room there is for the massive heat to escape.
Well, without a way to cool it, wouldn't the friction just, I don't know, melt everything?
Almost instantly, yeah. The drill bit would literally weld itself to the inside of the component.
Oh, wow.
So that's why manufacturers use a process called gun drilling. It forces high-pressure coolant right through the tool itself.
Wait, through the actual tool?
Exactly. So it's constantly flushing out the heat and the metal chips while maintaining a perfectly straight line.
So it's kind of like a marathon runner chugging water while sprinting just to keep the system from overheating.
That is a great way to put it. But getting a straight tunnel is really just the start. You also need the exact right size.
Right.
And that's where reaming comes in. Gun drilling blasts through the material, but reaming uses multi-edge tools to gently shave off, microscopic layers. It hits what engineers call an H7 clearance fit.
Which basically means the gap between that hole and whatever part goes into it is so unimaginably tight, they slide together perfectly without wobbling.
Precisely.
So we have a perfectly sized hole.
Mm.
But if the placement is off even slightly, everything falls apart,
Yeah.
right?
Yeah, and that is where jig boring enters the picture. This process controls the exact distance between holes. We're talking about maintaining a 5-micron tolerance on the center distance of planet gears.
Wait, 5 microns? That's roughly the size of a single red blood cell. How does a massive drill not wander off target by a single blood cell?
It relies on massively rigid frames and precise thermal control. I mean, the machine itself cannot expand from heat or it misses the mark.
That's crazy to think about.
It really is, because if that gear distance is off by a hair, the uneven wear will eventually tear the entire transmission apart.
So the hole is perfectly placed and perfectly sized. But if a steel gear spins inside it at high speeds, it's going to seize up from friction. How do we prevent that?
So they use a process called honing. It uses a rotating whetstone to correct geometric errors inside the housing bores, but it also deliberately creates a crisscross scratch pattern on the surface.
Wait, usually scratches on metal are a bad thing, so we are intentionally scoring the metal just to create tiny oil reservoirs for lubrication.
We are, yeah. It sounds counterintuitive, but those microscopic grooves hold on to the oil.
Ah, I see.
When a moving part slides through, that crosshatch pattern ensures it glides on a microscopic cushion of lubricant instead of grinding metal on metal.
That makes perfect sense. But I mean, all this precision means nothing if the metal simply fails under the weight of operation. How do they toughen it up?
To fortify the metal, they use roller burnishing. It's totally different from the other techniques because there's no cutting involved at all.
No cutting.
None. It's a cold extrusion process. That means they use extreme rolling pressure to physically squeeze the surface.
Wait, squeeze solid metal? Instead of shaving wood away, is this like packing a snowball tighter and tighter until the outside turns into a hard, unbreakable shell of ice?
Yes, that's a perfect analogy. You are compressing the crystalline structure of the metal itself. It closes up microscopic surface vulnerabilities, so the component, like a bearing seat, can withstand massive real-world loads without fatiguing.
We've taken you from drilling deep channels to packing solid metal into unbreakable shells. These aren't just vocabulary words for engineers.
No, not at all. They are the exact physical processes that keep the mechanized world spinning safely around you.
Right. Without them, our smooth, effortless technology grinds to an immediate halt. But it leaves you with a fascinating question to consider.
Oh, what's that?
Well, we are already engineering machinery down to 5-micron tolerances and intentionally designing